Hello, everyone, and welcome to Lecture 11 of Data 102. In the previous lecture, we introduced two new types of regression, Poisson regression and negative binomial regression. And then we saw that both of these new types of regression, together with your favorite linear regression and logistic regression, are all instances of this broad class of models called generalized linear models. And then we showed you some very interesting Python packages that allowed you to fit these models very conveniently from both a frequentist perspective as well as a Bayesian perspective. Now, the topic of today's lecture is model checking for GLMs. If you think back to the very first lecture of this course, we told you, if you remember, we told you about the two themes that are going to govern this, all the topics in this course. One theme was about decision-making using models, and the second theme was about modeling in the real world, and in other words, how to think about the very important relationship between the models that we fit and the real phenomena that we're trying to model. Now, the whole point of model checking is that modeling is not a linear process, but it really is a cyclic process. So after we fit our models, in other words, after we perform estimation, we don't stop there. We don't want to stop there, but instead we want to check our models and criticize them, and to see whether whether they perform well or not. And in the light of this criticism, we want to revise the models. So we want to improve the models in certain areas where they don't perform so well, and then perhaps we can improve them and we can fit the data better and make better predictions. Okay, and I just want to say that understanding all the subtleties of this process is extremely important, and this is what really allows you to level up your skills from being a beginner data scientist to an intermediate data scientist. Okay, so now let's take a look at our agenda for today. So here's a lecture overview. So we're going to start by taking a high-level view of GLMs. Okay, so GLMs are actually just types of supervised learning models. So I'm going to do a review of supervised learning and try to contextualize GLMs in this sense. And then we're going to compare GLMs versus black box models that you might be familiar with, like neural nets and random forests. Okay, and then we're going to resume a topic that we started in the last lecture, which is model interpretations. So we're going to talk more about how to interpret GLMs when the model is correct. And more importantly, we're going to talk about how to interpret GLMs when the model is wrong. All right, so I'm saying this is more important because in the real world, most of the time, or in fact, all of the time, the model that you prescribe is not going to be, it's going to be wrong in some respect. Right, so there's this famous saying by this famous statistician George Box, who said that all models are wrong, but some models are useful. Okay, so we want to think about how to make use of models even when they are wrong. Okay, and then we're going to get into the real meat of today's lecture and ask the very important question of what actually makes a good model. Okay, so we're going to introduce or reintroduce two very important notions, which are goodness of fit and generalization. And these are two desirable properties that we want for our models. Okay, and we're going to talk about how to achieve these, or how to get better at these two objectives by either expanding our model or contracting our model in the context of GLMs. Okay, and then we're going to talk about how to do goodness of fit checks for frequentist GLMs as well as for Bayesian GLMs. So just to note that for Bayesian GLMs, goodness of fit checks are also known by the term posterior predictive checks. Okay, so these two last topics probably are not so common in the data science education, but we feel that they are extremely important. And we hope that after this lecture, you get a very good understanding of how to use them in your future work. GLMs are actually a classical topic in statistics. And in several departments, there are entire semester-long courses about GLMs. So you can spend the entire semester learning about it. We don't have time to do that in this course. And furthermore, some of the topics I think are pretty outdated So instead, we're going to spend maybe 5 minutes taking a 10,000 feet view of GLMs. Okay, so let's recap a little bit of what we learned from the last lecture. So a GLM has 3 components, all right? So it has a systematic component comprising the design matrix X that contains all the data, and our vector of coefficients beta, which will give you the weights attached to every feature. And then there's a random component, which is going to be the noise distribution family, or in other words, it's going to be the family that governs how the response labels Y are going to vary depending on what the Xi and beta values are. Okay, and then connecting both the systematic and random components is a link function G. And this G is what's going to give you the relationship that G applied to the conditional mean of Yi given Xi is equal to Xi transpose beta. Okay, so these were the 3 components of GLMs that we saw in the previous lecture. So now let me rewrite the last expression in perhaps a more convenient fashion. Okay, so we can rewrite it in this way, which is that Yi, the label, is given by G inverse applied to the value Xi transpose beta, and then plus epsilon I, where epsilon I is some noise term that has conditional mean equal to 0. All right, so if you think about it for a moment, you see that this is equivalent to the definition of GLMs that I wrote above, and also that you saw in the previous lecture. All right, and now in this format, we can see more clearly the relationship between, or the analogy between a general GLM and a linear regression model, right? So in the case of linear regression, the link function is identity, so G inverse is also the identity. And we typically assume that the noise is Gaussian, so epsilon I is just going to be Gaussian with variance sigma squared. And then in that case, so Y is equal to simply just Xi transpose beta plus epsilon I. And in that case, the log likelihood of this model for the GLM is going to be simply equivalent to the squared loss function, which is typically what we minimize in order to fit a linear regression model. Okay? So now for a general GLM, say for Poisson regression, then G inverse is no longer the identity, right? So for Poisson, this is going to be the exponential function. And then not only that, epsilon I is also going to be different. So it's no longer Gaussian, but it's going to be Poisson noise. All right. So it's Poisson noise that has been recentered so that it's mean 0. But then now we see that epsilon I is now no longer going to be the same for every I. It's going to be some distribution that depends on what Xi transpose beta is, right? Because there will be the mean of the Poisson, which will also be the same as its variance. Okay, so this is a brief recap of how we define GLMs. And maybe one way to say what we did is that we've defined a data generating model, right? So we've defined a way of generating labels Yi given our data matrix X. Okay, so even though what we've said so far is simply a mathematical object, right? So there's no relationship to the real world. Nonetheless, we can try to fit the model to any collection of data that we see. Okay, so long as we see some collection of data X with labels Y, it doesn't have to be generated from a GLM or from anything for that matter. We can still fit a GLM to the data. Okay, it may not be a good fit, but we can still do it. And in fitting the GLM, what we're doing is to try to estimate the parameter beta of the GLM. Okay, and now the interesting thing happens. Okay, so now after we estimated beta to get some estimate beta hat. If you recall from the previous slide, beta is all we need to define the regression function for our GLM, right? So in other words, given Xi, given some new data point Xi, we can try to predict this label through the function to the equation G inverse applied to Xi transpose beta hat. Okay, and that's going to give us our predicted label Yi hat. Okay, so this should start to look very familiar to you guys. Okay, so this is simply what you get from a supervised learning model, right? So recall what we do in supervised learning. So after we have a model, we feed in a feature vector X, and then the model is going to spit out an output label Y hat. Okay, and that is exactly what a GLM is going to give you. Right, so if you took a machine learning course, you would probably have learned about various types of black box models, or so-called black box models like neural networks, random forests, and gradient boosted trees. And the reason why we call these black box models is that it's hard to really understand what's going on inside them, right? We just run sklearn, we write sklearn.fit, and boom, it fits the model's fit, and then we can get predictions. All right, and so there's a lot of very, very recent and important research that tries to unravel these black boxes. But on the other hand, we can also think about other classes of models like GLMs, which are essentially white boxes or gray boxes. Okay, so in these models, we have parameters beta, or in other cases, it could be other parameters. But the common theme is that these are very interpretable. So we know exactly what the coefficients mean, as explained in the previous lecture. Okay, and this is a very useful property to have. Okay, so let's talk a little bit about what the supervised learning pipeline is that you learn in an introductory machine learning course. All right, so there are 4 steps. In the first step, we want to do data splitting. Okay, and we want to do random data splitting. Okay, so we run np.random.choice or something like that. And then we take all the data, we typically split it into 3 portions. Okay, so we have a training set, a validation set, and a test set. And now after we split our data, we can go to step 2, which is where we start to fit all of our models. And as you learned, typically you fit a whole bunch of different models. And in order to fit the model, we need to specify a loss function, right? And if you have different loss functions, you're going to fit different models. So after you fit your models, what happens? Okay, so we need to do model selection. We need to find the best model or find the best of hyperparameters. And you do this using the validation set. Okay, so we evaluate the model performance on the validation set using the same loss function. Maybe you could use a different one, but typically use the same one. And then we use this to compute the validation set loss for all the different models. And then we pick the model with the smallest loss or the smallest risk. Okay, and in this case, we get some model K. And now after we select the model, this is the model that we pick, and we can then test the final performance of this model on the test set. Okay, again, using the same loss function. And then depending on the loss function that we use, we're going to get some performance metrics. So if you're using the mean squared, the squared error loss, we're going to get the MSE. And if you're a data scientist working for some company or even in academia, this is the number that we report to our boss. Okay, so this is the standard supervised learning pipeline. This pipeline has turned out to be very simple and yet very powerful. Nonetheless, it has several very important drawbacks. First, this requires a lot of data. And that is because when you split our data set into a training set, a validation set, and test set, our training set is going to be only a small proportion of the entire data set, and we have a lot less data in order that we can use to train our models. All right, so this is a very severe limitation when we have very little data, and so every data point is precious. Secondly, under this pipeline, we compare models using just a single number, which is going to be your average loss over either the validation set or the test set. Okay, so this may be sufficient in certain instances, but it still gives you very little information, and it doesn't really give you very much insight into how to diagnose whether or where your model has problems, and so how to improve upon it. Okay, so this is going to be an impediment to our cyclic view of how data analysis should be done. All right, so now let's talk a bit about the pros and cons of GLMs versus black box models that we typically use in the supervised learning pipeline. Okay, so what are the pros of GLMs? Okay, so GLMs actually work really well and when you have not that much data. And that is because it allows us to make use of subject matter knowledge. Okay, so if you're talking to some expert about some phenomenon, they can tell you about what are some very natural assumptions of that phenomenon, and you can try to build it into your model in order to using either priors or the way in which you parameterize the model. And this will allow you to increase your sample efficiency. And not only that, it allows you to extrapolate and make predictions for data that is very unlike the data that you have used to train the model. Okay, and this is something that may not be possible for other black box models. And this is because then some models like neural networks and random forests are so-called interpolation methods, meaning that they interpolate their data pretty well, and so they can predict pretty well for any new data point that resembles the data that you've already trained the model on. But it's very hard for them to extrapolate to new data, which is very far away from data points that you've already seen. Okay, and the next advantage of GLMs is that they're very naturally interpretable. And this is because they come with these beta coefficient vectors, right? And we know how to interpret these beta coefficient vectors. They just tell you how much the model predictions change as you change the value xi for some feature for that particular sample. Okay, for black box models, we don't have parameters that can be interpreted in such a fashion, right? So there's some very recent work about how to try to get around this, but it's still, it's still in early stages and still very difficult. So GLMs, this interpretability aspect of GLMs is a very important advantage. Lastly, GLMs, whether in the Bayesian setting or the frequentist setting, come with some very natural methods for how to perform uncertainty quantification, right? And this is very important because whenever you have a model and you make predictions, you're not just interested in the values of the predictions themselves, you also want to know how much you can trust the model, okay? So if some model is telling me that, this particular surgery has like a 2% risk of death, I want to know, whether it's just 2% plus minus 0.5%, or is this like 2% plus minus 10%, for instance. So that's going to make a very big difference in terms of the decision I'm going to make. Okay, but GLMs are not all good. There are definitely some limitations. So firstly, they are definitely a lot less flexible than black box models because they are very constrained. So initially, if you fit just the very first model you fit on data may not actually fit the data well enough. So, and that brings us to the second point, which is that you can actually improve the model, but it requires a lot more trial and error. Okay, so you need to be a lot more you need to be a lot more careful and a lot more skilled in order to fit GLMs compared to black box models. In this video, I want to introduce this very influential paper by Leo Breiman. Leo Breiman was a professor in the Berkeley Statistics Department, and he was a very interesting figure who led a very interesting life. You can read all about his life on Wikipedia. Now, he was famous for many things. And perhaps the two things that he's most famous for are, firstly, the invention of the random forest algorithm, and secondly, for writing precisely this paper. Okay, so as you can see, this paper was published in 2001, nearly 20 years ago. And back then, GLMs were the pride of the statistics community. There were many people who were doing work on this topic, but as you know, the GLMs require some data generating model, and most of this work was all in the context of assuming that this data model was true. Now, Leo Breiman came along and said, hey, there's this other new paradigm called machine learning, and this new paradigm is purely algorithmic, all right? So we don't care about the data model. And guess what? It turns out that these machine learning models actually make better predictions than the old statistics models that were popular in the statistics community at the time. All right, so as you can predict, this provoked a lot of very intense debates. But in the 20 years hence, it seems like Leo Breiman has been vindicated, right? So machine learning has now become super popular and super influential, and perhaps a lot more so than the old statistics models and paradigms. Okay, And in some sense, this is all true to a first degree of approximation. Okay, so GLMs are indeed, a lot more tricky to use, but if you understand them well and also how to use them despite their underlying assumptions about the data model not being correct, then they can still be very useful, as we saw, in the previous video. All right, so learning about them can give you a very important tool in your toolkit. In this video, I just want to show a simple example where fitting a GLM does better than fitting a black box model. Okay, so this example is going to be about COVID. If you remember, in the early days of the COVID epidemic around this time last year, there was a lot of interest in trying to predict case and death numbers at the county level. And this was for many reasons. One reason was try to better plan what kinds of social distancing policies to put in place. And another reason was to try to decide how to allocate medical resources, right? So if there were going to be more deaths or cases in some county, we want to give that county even more resources and send more medical personnel over there. So let's look at some of that data. Okay, so here I have COVID case and death count over a period of 25 days from Cook County, and Cook County is a county that contains Chicago. So as you can see in this data set, I have case numbers and death numbers, and days will be the number of days after February 28th last year. Okay, so I'm going to try to fit, so first I'm going to do a data split. So we're going to split the data into the first 20 days, which we're going to use as the training set. And then I'm going to hold out the other 5 days to act as a test set to evaluate our models. Okay, and then we're going to fit a GLM and we're going to fit a random forest and compare the performance of these two different models. First, let's do a plot of the case counts for the training set. And as you can see, it looks like there's some form of exponential increase. All right. And this means that having a GLM, which is either a Poisson or a negative binomial model, is very appropriate because we call that the link function as the exponential function. Okay, so let's fit a negative binomial model. Okay, and similarly, we can just fit a random forest model, which we get from sklearn. And now, following the standard machine learning paradigm, we can compute the error on both of these two data sets. So I'm using the mean squared log error, which is appropriate for this sort of data set because of the exponential increase. So let's compute it. And we see that the error is 1.9 for the random forest model and 0.6 for the negative binomial model. Okay, so the negative binomial model wins. Okay, so let's try to see what's happening and to see why this is the case. Okay, so here, I'm going to first plot the actual case counts for all the days, both in the training set and the test set. And then I'm going to overlay this with a plot of the predictions from my negative binomial model. Okay, so as you can see, right, so so for the training set, we saw up to day 19 up to here, and then the remaining 5 days continued this exponential trend, and that is pretty accurately modeled by the negative binomial model. So if anything, it's sort of underestimating this exponential increase. On the other hand, if we plot the predictions for the random forest model, something strange is happening. Okay, so it kind of fits the training data perfectly, right? So it just passes through all of these points. But at the end of the training set, it levels off, right? And any predictions for future time points is constant. It's constant at the prediction for day 19. Okay, and why is this the case? So if you know a bit about how random forest works, it works by binning the data points and puts data points into bins, and then the predicted label or predicted value for the outcome is simply going to be the average over these bins. Okay, so this is one feature of being a so-called interpolation algorithm, and this means that it just does not extrapolate very well to the new data points that are far away from what you've already seen. Yeah, so that's why you mix this huge error over here and does not account for these exponential trends. Okay, so what's the takeaway? What's the moral of the story here? So the random forest, you see, was something that we didn't tune, something that works pretty well as a first approximation for many different settings, but it doesn't actually perform so well in this setting. On the other hand, it's not because it's not just because this COVID case prediction problem is hard. It's also because we have not taken into account the basic underlying scientific properties of this problem, right? So if you talk to some epidemiologists, they will tell you that epidemics follow this exponential trend. And using knowledge, we knew that by fitting a negative binomial model or maybe even for some model, this allows us to extrapolate a lot better and get better prediction performance for future days. In this video, we are going to revisit the topic of GLM interpretations that we studied upon in the previous lecture. So let's revisit this demo about the wind turbines dataset in which we use the stats models package to fit a negative binomial model. Okay, so when we fit the model, we get this output. And as I said in the last lecture, we can use the coefficients in the output and plug it into the original GLM equation to try to form an interpretation. Okay, and when we do that, we get an equation of the form: the log of the turbine speed is equal to 0.24 times the difference between the year and 2000 plus an intercept of 4.2. All right, so how do we interpret this in words? Okay, so to do so, we want to take the exponential of both sides. And so this is going to tell us that the turbine speed is going to be, the number of turbine speed is going to increase by roughly 24% each year on average. Okay, and this is because the 0.24 over here becomes the continuous rate of growth once you take an exponential of the right-hand side. Okay, and in the last lecture, we stopped here. But now I want to draw your attention to this approximation sign. Okay, so if this were equality, then the interpretation that we just wrote down would be fair. But because this is an approximation, we have to be very careful about in what sense this is an approximation. Okay, so there are going to be three different ways in which this equation is not exact. Okay, so the first sense in which this is the case is pretty dumb. It's just rounding error. So recall on the previous slide, we saw that the coefficients were not exactly 0.24 and 4.2. They had other trailing digits, but I just truncated it to 2 digits, and that's going to introduce some error. The next source of approximation is the noise in the response. Okay, so what I mean by this is that in the original GLM equation, so log was a length function for negative binomial, but we apply the length function to the expected response and not the actual response. Okay, so there's an expectation sign that's missing over here. Okay, and for the GLM equation, it says that the log of the expectation is equal to this function here on the right-hand side. Okay, and once we drop the expectation, we have to account for there being some noise in how the responses are generated. Okay, so in some years, there might be a bigger increase in the number of turbines. In other years, there might be less, just because of pure chance. And this is under the GLM model. Okay, so this contributes to the approximation, but in some sense, we have already accounted for this by tagging on the words "on average" at the end of this sentence. Okay, so once we take an expectation over that randomness in the response, then we remove that. We remove the sense in which this adds to the approximation. But there's a third way in which this equation here is an approximation, and this is going to be the main topic of our discussion today. Okay, and that is going to be estimation error. Okay, so what we mean by estimation error is that the GLM model that we fit is not necessarily going to be the same as the model that generates the data. All right, and this can happen in two different ways. So let's talk about the first way. So the first, and for the first way, we have to assume that we have a correct model. So what does a correct model mean? So it means that for, so it means that there is a true beta 0, or sometimes spelled beta naught, such that the GLM model with coefficient vector beta naught is actually the true data generating model, right? So in other words, we generate the yi's in this fashion, right? So we have a coefficient vector beta 0, and yi's are just going to be G inverse of SI transpose beta 0 plus some noise epsilon I, right? And this is how the yi's are actually generated. Okay, but note that we don't actually observe beta 0. This is an assumption that this is the data generated model, not the model that we fit. And then when we try to fit the model, we're going to get some estimate beta hat, right? And we don't actually get beta 0 because there's going to be some noise, the epsilon i's, in our observations of the y-i's. And this noise is going to make it impossible for us to actually know the true beta 0, and all we can hope for is an approximation. However, once we assume that the model is correct, then there is some heavy-duty statistics theory that helps us to bound the estimation error, which is beta hat minus beta 0. Okay, and this heavy-duty statistics machinery is going to tell us that we have some kind of central limit theorem type result, which allows us to say that asymptotically, the estimation error is going to be a multivariate Gaussian with covariance equal to this matrix here, which is the inverse of the so-called Fisher information matrix. Okay, so what this is really beyond the scope of this course. I'm just writing this down here for you to be aware of it. And the takeaway is that if the model is correct, we are able to bound the estimation error between beta hat and beta and the true coefficient beta 0 using some statistics theory. Okay, so why is this important? Okay, so this is important because what we really want to interpret is the true beta 0. Okay, but what we see is beta hat instead. So any interpretation of beta hat must be in reference, must take into account this error, right? So it must be in reference also to the amount to which beta hat differs from beta 0. All right. And so when we run our stats models package, we will get, so over here I'm highlighting some part of the output, which is the standard error. And I just want to point out that this standard error is generated using the theory that I talked about in the previous slide. Okay. And there's and we know this because over here it says that the covariance type is a non-robust covariance type, which is that it's another way of saying that they're using this statistics theory that I talked about in the previous slide. Okay, so now that we know the standard error, we can go ahead and use that to get error bounds for our coefficients. And so this says that our true coefficient for the year variable, for the year feature, is going to be somewhere between 0.24 minus 0.08, which is 2 standard deviations below, and 0.24 plus 0.08, which is 2 standard deviations above. Okay. And based on that, we can update our interpretation. So now we say that the number of turbines built increases by roughly 16 to 32% each year on average. Okay. And so we've updated the previous 24% to a range, 16% to 32%, by taking into account the fact that the coefficient vector beta hat that we observe is only an approximation of the true coefficient vector beta 0. In the previous video, we talked about how to think about interpretations when the GLM model is correct. Now let's examine what to do in the case where the GLM model is wrong, or in other words, when there is no true beta naught and the distribution that's generating our data is simply not part of our GLM family. Okay, so let me try to illustrate what can go wrong by using the wind turbines data set that we've been using. And this time, I'm going to use the wind turbine data from the state of California instead of the state of Oklahoma. Okay, so I'm going to go ahead and make 2 plots of the total number of wind turbines built against the year. Okay, so this is the number of years since the year 2000. And the first plot is going to be this relationship on the linear scale. And the second plot is going to be this relationship on the log scale. Okay, so you can see that neither of these 2 plots have a linear relationship. And so the fact that the first on the regular scale, this is not linear, means that the linear regression model is misspecified. And the fact that this is not linear, even on a log scale, means that the Poisson and negative binomial models are also misspecified. Okay, but despite the misspecification, we can still go ahead and fit the two models. Okay, so let's go ahead and do that. And here I'm plotting the results. Okay, so the black dots over here are going to be our observations of the actual number of wind turbines built for each year. The orange line is going to be my model predictions using my linear model, and the blue curve is going to be my model predictions using the negative binomial model. Okay, so as you can see, neither of these two curves gives us a good fit. And if you try to interpret them, right, so if you try to interpret the negative binomial model, as we try to do for the OK wind turbines data set, we're going to get something that's kind of nonsense, right? So it's going to say something like, so let's see what the coefficient is. There's negative binomial. Yeah, so it says the coefficient is 0.15. So this, if we were to interpret it like in the previous case, it's going to say something along the lines of the number of wind turbines built increases by roughly 15% each year. But then it's clearly not the case because there's so much heterogeneity and the patterns and this data. Okay, so the takeaway is that we need to be very careful about interpreting our GLM models when the model is not actually a good fit for the data. Okay, but in some cases, the model may actually still be meaningful despite it not being a perfect fit. Okay, so let's go back to the slides and let me try to elaborate a bit more about what they mean. Okay, so to recap, what is model misspecification? It is what happens when the data generating distribution for the labels Y is what happens when this does not actually lie inside the GLM family that we're trying to fit, whether it's linear regression or Poisson regression or something else. However, even when this is the case, there are under some assumptions. So I'm writing this I'm making the text here small because I guess for the scope of this class, we don't have to worry too much about this. But under some assumptions, we can still fit our GLM model to the data. And if we have more and more data from the same distribution Q, which doesn't actually lie in our GLM family, the fit coefficients that we get from fitting our model to more and more data is actually going to converge to something. Okay, so it's estimating something. It's not estimating the true model, but instead it's estimating what is called in the literature the projected model. Okay, and this is, in other words, the closest distribution in our GLM family, P, okay, so P parameterized by beta, and it's going to be the closest such distribution to the data generating distribution. Okay, so for the linear regression case, so if we try to fit a linear regression model, we're going to get the best fit linear predictor. Okay, so it's not actually the true data generating model, but it's something that kind of makes sense in the sense of being a best approximation from a certain class of models. All right, and so our interpretations can be with respect to this property. Okay, so in that sense, even though the model may not be a good fit, we can still try to interpret it in terms of its approximation. Okay, so in summary, this model that we get might actually be meaningful to interpret, or it may not be. So it really depends on your circumstances. And so you have to really think about whether it's worth doing or not. Okay, and the other takeaway is that we really do have to care about model misspecification, and we need ways of trying to detect it and diagnose it. Okay, and that will be the topic of some future videos. So far, we've been talking about model misspecification from a frequentist point of view. Now let's see what changes when we want to think like a Bayesian instead. So recall that Bayesianism is philosophically different from frequentism. And so the starting point of our discussion is going to be a little bit different, right? So first, in Bayesianism, we do not assume a true model beta naught. So this means that it doesn't actually matter, in some sense, it doesn't actually matter if our model is misspecified, because all of our probabilities are simply going to be in terms of our beliefs, and they do not actually have to reflect some kind of true description of how the world is like. right? So whatever data we get, wherever it comes from, we can fit our model, and then the fit model is simply going to be an expression of our posterior beliefs. Okay, so what are the implications of this? Okay, so this means that even if a model is not a good fit, it's actually not the end of the world. And this is sort of, a little bit in contrast to what happens under the frequentist paradigm. Okay, so if the model is not a good fit, perhaps that's fine because we allow for some assumptions that is not revealed in the data. Okay, so and whatever posterior belief that we have is going to be some kind of interpolation between the data that we observe and the other assumptions that we want to make. Okay, so we can live with a poor fit in a way that possibly we cannot do if we were trying to be frequentist. However, if you think like this, it's easy to become a little bit solipsistic, right? Meaning that everything seems to be circular and we just, there's no relationship with the real world. Everything is just in terms of our beliefs. And then different people can have different beliefs. So, and then maybe there's no way to try to say whose beliefs are better. So we need some way of doing that. We need some way of tying ourselves to the real world. And so increasingly people are trying to think about this in a very rigorous fashion. And I think one way to summarize some of the observations is that if the model is actually not a good fit to the real world, we need to be able to justify why. Okay, so it doesn't mean that the model is useless, but we should at least try to question. Yeah, so if we need a way of, so if the model is not a good fit, we had to think about in what sense it's not a good fit, and we had to ask whether or not this lack of fit is justified based on the other assumptions that we're making about the phenomenon that we're trying to model. Now that we've spent some time talking about some of the consequences of model misspecification, let's move on to ask the question, what actually makes a good model? Okay, so two of the things that we want to desire from the model are goodness of fit and generalization. So let's talk about these two. Okay, so what's goodness of fit? Goodness of fit is actually how well the model fits the training data. Okay, and if you are using a black box machine learning model, this is something you often take for granted because these models are so flexible that oftentimes the training loss is going to be 0 or pretty close to 0. Okay, so you only worry about generalization. But this is not the case for more constrained models like GLMs. Okay, so for GLMs, the training loss may actually be pretty high, and that's something, if so, you want to worry about that. And recall that for GLMs, the loss function is just going to be what's given to you by the negative log likelihood. So training loss is very connected. In fact, it's going to be the same thing as how probable your data is given the likelihood. Okay, but this one number is not the only thing you can do to try to evaluate goodness of fit. Another thing you can do is to do a visual inspection. And this is exactly what we did for the demo for the wind turbines data set. So there we plotted the predictions using the linear model and the negative binomial model, and we used the graph to try to conclude that these two models did not actually fit the data so well. A third thing you might do is to use other forms or other statistics to try to quantify how well the model fits data. Okay, some of these statistics are deviance and chi-squared. Okay, so we don't have to worry about them too much in the context of this class. This is just good to know that these exist. Okay, so we might talk a little bit more about them in a future video. All right, and once you have goodness of fit, okay, we're not satisfied because this means that your model just fits the training data well. We want it to also generalize to data that we don't see, and this is going to be given to us by the test set. Okay, so we can try to evaluate this in terms of the test loss, but again, it's not the only way, so the other things that you can do as well. All right, but we're not going to talk about that in this video. All right, so what can you do if your model does not fit the data so well, as was the case in our previous demo? Okay, so we can actually, so the GLM model that we have is not the final model, so we can always try to change it, right? So we can either expand it or contract it. Okay, so what do I mean by this? How do you expand the model? Okay, so one way to expand the model is to add new features. So basically expanding the model means making it more complex and more expressive and allow you to fit the data better. Okay, and by adding new features, you can do this. Okay, so this is sometimes called feature engineering. So suppose you start with two features, x1 and x2. we can create new features by taking the squares of x1, x2, the product between them, and then cubes of the features, and so on and so forth. Okay, so we can keep adding new features which are algebraic combinations or even other functions of the original features that we have. All right, and so by doing so, we convert a linear model into a quadratic model or some even more complex model. So that's one way. Another way is to change the noise model that we have in our GLM to make it more flexible. Okay, so we've seen some examples of this. So we change the Gaussian to a t-distribution in some ways, then making the noise distribution more flexible. And we're doing the same thing when we change the Poisson model to the negative binomial model. Okay, and we can also go in the reverse direction, right? So if a model is too expressive, we may want to contract it by dropping features. So why would we want to do something like that? That's because there's a balance between underfitting and overfitting, right? So as we expand the model, we increase its complexity. And this means that it's more flexible and we can fit the data better, which means that in some sense, it's less bias. However, the better it fits the data, the better it also fits noise in the data, which means that there's more variance. Okay, so goodness of fit goes up, but generalization error may actually go down. All right. And so in a lot of textbooks about machine learning and statistics, you see this bias variance trade-off curve. And so let's try to interpret this curve. So on the x-axis, you have model complexity. And the more increased complexity, bias goes down. So bias is this blue curve here. But on the other hand, variance is going to go up. Okay, and the total error, and this total error will be the test error, is going to be the sum of the variance plus the bias squared. All right. And this is exactly true for squared laws. And in some sense, this is heuristically true for other loss functions. Okay, so what you really want to find here is the sweet spot. Okay, so you want to keep expanding the model until we hit this sweet spot here, which gives us the minimum total error. Let's now talk about a few ways of trying to evaluate goodness of fit for frequentist GLMs. So on this slide, I am displaying the output of fitting a negative binomial model using the stats model package. Okay, so as you can see, this is sort of like an information overload. There are many quantities here, some of which we have not yet discussed. In this video, I'm going to spend some time talking about these three quantities on the right-hand side, the log likelihood, the deviance, and the Pearson chi-squared. And all three of these are quantities that you can use to try to evaluate the goodness of fit of your model. Okay, so first, what is the log likelihood? So recall that the way we fit our GLM is to maximize the likelihood. So in other words, we want to find the parameter beta that maximizes the likelihood of our data. Okay, so this is the so-called maximum likelihood principle. But maximizing the likelihood is equivalent to maximizing the log of the likelihood, right? And sometimes it's a lot easier to maximize the logarithm of the likelihood instead of the original function. Okay, so why is this the case? Right, so if you think back to the Gaussian model, if the likelihood is a Gaussian, taking the logarithm of that will give you just the negative of the squared loss, which makes it a lot easier to minimize or maximize. All right, so in other words, the bigger the value of the log likelihood, the better the fit of your model. Equivalently, because the log likelihood is a function that we try to maximize, then you can think of this as a negative of the training loss, right? So under the classical machine learning paradigm, the smaller the training loss, the better the model fits, or in other words, the bigger the negative of it, the better the model fits. Okay, so how about deviance and Pearson chi-squareds? So I'm not going to go into the details about how these are defined because it's kind of complex and beyond the scope of this course. All you need to know is that these are statistics for doing hypothesis testing. And the hypothesis that we want to test here is whether or not the model fits the data well. Okay, so you can convert these into p-values to test this hypothesis, but in this course, we're not going to talk about how to do that. Okay, so under some assumptions, we can use this to perform a test about whether the model is a good fit, but it relies on these tricky assumptions, which are really perhaps not really applicable or so reasonable in real data settings. So in some sense, you can think of these as being a little bit outdated and not so important to know. Okay, for our purposes, we just want to know that the smaller the deviance or the smaller the Pearson chi-squared, the better the fit. So we can use this piece of information to try to compare different models. All right, so let's do that now. So on this slide, I'm displaying in tandem the results of the negative binomial model and the Poisson model fitted to the wind turbines data set. And we can compare the values of log likelihood, deviance, and Pearson chi-squared for both models. So as you can see, the log likelihood for the negative binomial model is a lot, it's less negative, so it's larger than the likelihood for the Poisson model, which implies that the negative binomial model is a better fit, as we already knew from looking at the demo from the last lecture. And conversely, the deviance and the Pearson chi-squared are a lot smaller, in fact, by several orders of magnitude. Okay, so all in all, these three statistics tell us that the negative binomial model is a better fit. All right, so how about comparing the negative binomial to the Gaussian model? Okay, so here I switched the bottom panel to the results from fitting the Gaussian model. And surprisingly, it seems that now the deviance and the Pearson chi-squared are smaller compared to the Poisson case. And now the log likelihood is actually less negative than that of the negative binomial, okay? So it seems as if this implies that the linear model is actually an even better fit than the negative binomial. Okay, but something's a little bit fishy because we know that this is not actually the case. Okay, so what's wrong? So what is up over here is that in some sense, when we compare the negative binomial to the Gaussian model, these are kind of incomparable because the negative binomial assumes that the yi's are integer valued. Okay, so we have, in that case, our probability over the y's is going to be a discrete probability, right? So we're going to get a probability mass function. On the other hand, for the Gaussian case, we make no such assumption. We assume that the yi's are continuous. So now our likelihood as a function of the data is going to be a continuous function. It's going to be a density. Okay, so in that sense, these two numbers are incomparable, right? And likewise for the deviance and the Pearson chi-squared. Okay, so this is just the takeaway from this is that when we want to use these quantities to compare different models, we have to be very careful about what they mean and when they can be compared and when they cannot be compared. Let us move on to talking about goodness of fit checks for Bayesian GLRMs. So it happens that the most dominant paradigm in this area is the posterior predictive check. And this is a concept that was developed by Don Rubin and Andrew Gehman, who are two of the most famous and prominent statisticians of our time. So what's the basic idea? Here, I'm giving you a quote by Don Rubin. And if you want, you can pause the video for a few moments to read the text of this quote. But I'm just going to try to explain it in my own words. So what it says is that after you observe our data and fit a model, we can try to simulate new data from our model. And simulating the data will give you a hypothetical replication of the study. Okay, and now we can compare the original observed data to the artificial simulated data. And if the model is a good fit, then both of these two, both the real data and the simulated data should be similar. Okay, but being similar is quite a vague notion. So we want to make it rigorous and quantify it and make it more specific. In this code, Don Rubin is only being a little bit more specific. So he says that we want it to be similar in some relevant ways. And what statisticians do is that they develop some quantitative measures or discrepancies to try to quantify those. Okay, but we're going to do something that is more visual and more appropriate for the level of this course. Okay, and how are we going to do this? Okay, so we're Bayesian. So we want to do replications in a very specific way. And what we want to do is to condition on the data that we observe. Okay, so in other words, we want to use the posterior predictive distribution. So what is this? So this is something that we talked about in the previous lecture. And we get this. And okay, so first it's going to be distribution on the y values. So the distribution on the labels. And the way we get it is to take our density of y given x and beta and take an average of that with respect to the posterior distribution on beta. Okay, and just note that the y over here, so this should really be y rep. Okay, so the replicates. So this is a different y compared to y ops, which is the data that we actually observed. Okay. So now, how do we simulate from this distribution? And then that is actually pretty easy. So it's going to be a two-step process. First, we draw a sample of beta from the posterior, and then we condition on it and we draw a sample of y. Okay, and just to note that when we draw a sample of y, we're really drawing n different samples if we have n original observations because we want to repeat the entire study. All right, so y over here is actually a vector. Now, having done this, we want to repeat this b times to get to simulate repeating, doing a hypothetical replication of the study b times. Okay, so now let's go to a notebook demo. All right, so in this demo, we're going to go back to look at the Oklahoma turbines data set that we are pretty familiar with at this point. All right, and here, it really fitted the PyMC3 model for the Gaussian model, the Poisson model, and the negative binomial model. Okay, so all this code is copied and pasted from the lecture notebook from lecture 10. What's new over here is that we want to do a posterior predictive check, so we need to draw samples from the posterior predictive distribution. Okay, so it turns out that this is actually very easy using PyMC3 because PyMC3 has this sample posterior predictive method. All right. Okay, so if you want, you can read the documentation about this. Okay, so here I'm just showing you that it's very easy. Okay, so the code is really just an imitation of the code that we use to fit the PyMC3 model. So it's very similar. And we run it. So I already ran it in this notebook. And it's going to give us this object, Gaussian PPC, stands for Gaussian posterior predictive check. And now, what do we do? Okay, so first in this cell, I'm going to compute some. Okay, so let's take a look at this. So what's happening? I'm going to do this for the negative binomial. So here you can see that this is a dictionary with 3 entries, and it has an entry for each of the variables. Okay, so year over here is going to be the beta coefficient for the year feature. Intercept is going to be the intercept, and y will be our y replicates. Okay, and each of these is going to, okay, so year and intercept are just going to be vectors of length b, where b is the number of replications. Okay, so we can check over here what the shape is. Okay, so we did 2,000 replications. And then for y, we have 2,000 replications, but 17 observations. Okay, so this is going to be a 2,000 times 17 matrix. Okay, so what do we do? So I want to make some plots, but first I need to compute some intermediate values. So over here, for each of the models, I'm computing the regression function. Okay, but for every single replication, so each one of these 2,000 replications, I'm going to compute one regression function. Okay, and then compute the regression function by plugging in the values of beta. Okay, I'm going to plug in these values that I get from doing my PPC sampling. All right, so now if you take a look at this, what's the shape of this? Okay, so again, it's 2,000 times 17. This is because we have 2,000 replications And for each replication, it's going to give me my regression function that takes values at the 17 values, the 17 years that we have in our data set. All right, so now let's do a plot. Okay, so I run this and I get a plot. Okay, so let's try to interpret this. So the blue dots here are our data. So these are the actual observations of the total number of turbines built across 20 years. And now I want to talk a bit about what the green band and the orange band mean. Okay, so if you look closely, you see that there's an orange band that lies in the middle of the green band. Okay, so first let's talk about the green band. Okay, so the green band is about the simulated Y values. So recall that we have 2,000 replications, and each replication is going to give us a vector of 70 numbers, one number for each year. And here, even though the 20 years, I think 7 years are missing, so which is why we have 17 and not 20. Okay, so let's fix our attention at 1 year. Okay, so let's say year 5. Then we have 2,000 numbers because we have 2,000 replications of Y. Okay, and these 2,000 replications are values of Y that we should have seen if our model is our model is a good model. And now, how do we summarize these 2,000 numbers? So what we do is to do a density plot and find a region that contains 95% of the mass of this density, right? So this is the density of the simulated data. Okay, so in other words, what we're doing is finding a 95% credible interval for the posterior predictive distribution. Okay, so now that we have this region, this is going to give us the width of the band at this particular year. And then we just do the same thing for every year, okay? And so that's going to give us a green band. Okay, and so if our model were a good fit to our data, then each of the data points should really be lying within this band, right? So if it lies within this band, it means that it is similar to the other Y replication values that we've seen for that year. But in this plot, clearly that's not the case. Okay, so these data points are clearly far away from our band, which means that the model is not actually a good fit. Okay, so what's the orange band? Okay, the orange band is instead going to be quantify our uncertainty about the regression function. Okay, so why is there a difference between the regression function and the simulated Y values? That's because the Y values are always going to be simulated from the regression function plus some noise, simulation noise, okay? So that's why there's a difference between these two things. Okay, and what we want is not for the Y values to be similar to the regression function values, but we just want them to be similar to the other Y replication values. Okay, so now we really know that the Poisson model is not a good fit. Okay, so maybe I should have said earlier that I was doing this plot for the Poisson GLM. Okay, so now we can go ahead and do the same plot, but for the other GLMs that we fitted. So not only the Poisson model, but the Gaussian model and the negative binomial model. Okay, so I've already done that, and by doing that, I'm going to get this plot with 3 different panels. And the first panel is what we've already seen. The second panel is what we get by doing the same analysis for the Gaussian model. All right, and as you can see, there's a huge difference between what we got for the Poisson model and what we got for the Gaussian model. Okay, so on the one hand, now these data points lie within the green bands and even the orange bands, so that's pretty good. Okay, so this means that yeah, these points, the data points that we actually observe, seem to be lie within the most of the mass of the simulated data, so it means that it's pretty similar. But on the other hand, this means that our simulated data also has a big spread. So as you can see, if you look at the y-axis, for the Poisson model, it goes up to 6,000, but for the Gaussian model, it goes up to 80,000. So that's kind of crazy. All right, and when we go on to consider the negative binomial model, we see that it's sort of like the best of both worlds. Because on the one hand, the data points, once again, lie within this green band of the simulated data. But on the other hand, the width of these bands are actually not as big. So here you see that the y-axis only goes up to 20,000 and not to 80,000. Okay, so all in all, the takeaway from this, from doing our posterior predictive checks, is that the negative binomial model seems to be the best fit. And this concurs with also with the analysis that we did for the frequentist GLM, and also with all the discussion that we had today, as well as in the previous lecture. We've come to the end of today's lecture, and I just want to say a few words in summary. So at the stage that you guys are at in your data science education, you have probably already seen the supervised learning pipeline, and you know how to use sklearn. So it is as if that you have this big hammer that you can use to try to tackle and resolve many data science problems. Okay, and in some respect, this is true because this pipeline and sklearn package are both very powerful tools. But at the same time, not every problem that you come across can be thought of as a metaphorical nail that you can resolve using a big hammer. So instead, in order to upgrade yourself from being a beginner data scientist to an intermediate data scientist, we have to learn how to be a lot more circumspect about fitting models, and we need to change our paradigm to think about data analysis as a cyclic process. All right, and in this cyclic process, we need to know how to do criticism of our models. Okay, so we need to and this is something that we learned into this lecture, which in some degree. So we need to be able to criticize the models and see whether they fit the data well. And in so doing, we can try to improve them to make better predictions, as well as to try to give better and more accurate interpretations. Okay, and here are some resources that I found on GLMs and posterior predictive checks. So the difficulty level of these resources is probably beyond the level of this course, but I'm just putting them here for any of you who are interested in reading more.